this video is all about experiments. So our learning target is I can analyze experiments. Alright, so the purpose. An experiment is used primarily to identify causal relationships. Let's see. Here are the key components. Control and treatment groups to compare. You have to have both or it's not an experiment. Random assignment. Big deal. So random assignment of individuals to the control group or treatment group. Ideally, all other variables are controlled so that the impact of the treatment can be studied. The experiment can be replicated, which just means repeated, multiple times for accurate analysis of results. Okay, so when you do an experiment, there's a control group and there's a treatment group. So if you don't know what those mean, the control group is a randomly assigned group that receives no treatment. That's why they're the control. They're the one we're going to compare it to. The treatment group, a randomly assigned group that receives the treatment. I'm pretty sure I just spelled receives wrong. Yep. I before E except after C. Oh, that's embarrassing. Alright. So here's some related vocabulary. The treatment is the factor which is manipulated in the experiment. I'm going to say experiment group. The experimental unit, that is the individual unit to which treatments are applied. Alright. Then there's an explanatory variable. So that is the variable that explains the change in the response variable. Which brings us to our last vocabulary word, response variable. And that is the variable that is the focus of the experiment. Alright, so when we use these words, you need to understand what each of them are talking about. Okay, so look at these examples, and we're going to identify the treatment, the experimental unit, the explanatory variable, and the response variable. Researchers are studying the possible effects of vitamin C on health. They have 100 participants in their study. They give 50 randomly selected individuals 250 milligrams of vitamin C per day, and the other 50 individuals receive a placebo, which means it's just something that doesn't work. They test both sets of individuals at the end of the period of the experiment. So the treatment is going to be the 250 milligrams of vitamin C daily. Our experimental unit is going to be those 50 people. So I'm going to say 50 individuals receiving the vitamin C. Alright, our explanatory variable, that is our vitamin C. That's what we're looking at. And the response variable is just going to be overall health. So does vitamin C cause overall health benefits is what we're looking at. Alright. So for each of the examples below, identify the treatment, the experimental units, explanatory variable, and the response variable. A note about treatments over here is sometimes an experiment might have more than one treatment, so that's okay. For example, in the vitamin C study, researchers might have 2 treatments, 250 milligrams of vitamin C or 500 vitamin C. The explanatory variable then has multiple levels, so there can be more than one treatment, perfectly fine. You just have to read it. So I want you to try number 1, in 1, 2, 3. Alright, so here's what I got. I said the treatment was acupuncture. The experimental unit was 160 healthy women. The explanatory variable was acupuncture, and the response variable was pregnancy. So, if you disagree or you don't understand how I got any of that, let me know, message me. Alright, I want you to try number 2, same thing. I want you to pick out the treatment, experimental unit, explanatory variable, and response variable. Try that in 1, 2, 3. Alright, so here's what I got. So there were 2 treatments, brand A and brand B, which is perfectly fine. You can have more than one. The experimental unit, 40 student volunteers. The explanatory variable, deodorant brand. The response variable, rating of effectiveness by volunteers at the end of the day. So anything close to that, you're good. If you have any questions, send me a message. All right, let's try this third one. So same thing. Find the treatment, the experimental unit, explanatory variable, and response variable. Try that in 1, 2, 3. All right, so here's what I got. Treatment, review session, the experimental unit, students and AP stats, explanatory variable, the review session, response variable, test results following treatment. So if you have any questions, send me a message. Okay, so let's look at experiment design. So whenever possible, an experiment should be designed for replication, because you got to repeat it to make sure it actually worked, control, and randomization. This provides the clearest means for finding if there is a causal relationship. In addition to controlling for bias, researchers can employ randomized block design, and I'll tell you what that is in a minute. Completely randomized design, and this one you've probably heard of, double-blind design. Alright, so now I'm going to give you a definition for each of these, and I'll draw you a little diagram. Okay, so let's think about this. An experimenter wants to determine the effectiveness of a cold vaccine. Of the 1,000 volunteers, 500 will receive the vaccine and 500 will receive the placebo. The dependent variable is the number of colds reported in each treatment condition. What do the different designs look like in this case? So, based off of that experiment alone, let's look at the definitions from these 3 different experiment designs, and we'll look at a diagram, so if you're more of a visual person, maybe it makes more sense. Alright, so in a randomized block design, the experimenter divides subjects into subgroups, or blocks, and the subjects within these blocks are randomly assigned to treatment conditions. So here you have your 1,000 subjects, and then you have these different blocks, and then they have the different treatments. So that's your visual for that. I think it kind of helps. In the completely randomized design, subjects are randomly assigned to treatments, so pretty easy. So here's your 1,000 subjects, and then they're assigned a treatment. And then the last one is your blind and double-blind study. In a blind study, the participants don't know who is receiving a particular treatment. In a double-blind study, neither the subjects nor the experimenters know who is receiving a particular treatment. This procedure is utilized to prevent bias in research results. So you can look at the visual. Pretty easy to understand. I don't know why this extra thing is there. Sorry. Alright. So you can go back and pause the video if I went too fast. Sorry about that. And then the last thing you're going to do is we're going to do some examples. So there's 2 scenarios. There's 3, A, B, and C. For each of the scenarios, explain flaws you find in the design of the experiment, why these are flaws, and how to improve the design. If there is no design, design an experiment. Finally, if an experiment meets the conditions for good experimental design, indicate how it does. So look at this first one. We'll do it together. To see the effect of the use of calculators on test scores, a teacher let 25 students use calculators and 25 students not use calculators. The students decided which group they are in. All 50 students sat in the same room to take the test. The researcher analyzes the results. Okay, so let's think about the flaws. Okay, so the first thing that I noticed is that the subjects determine their treatment, which is never supposed to happen. And who would opt to do the calculator inaccurate? That's a little crazy to me anyways, whatever. And then also, the subjects know which group they're in because they selected it. No, that's weird, no. Which group they're in. Okay, so if we were going to improve it, I would say make it into a double blind. Because I don't think the students should be determining which ones they want to go into. And then students could be randomly sorted into treatment and placebo groups. So it needs to be random assortment into treatment and placebo groups. Alright. Yeah. And if you wanted to add stuff, you could, but those are the things that I see are flaws and then how we can improve them. So using that, I want you to try B. A market researcher wants to determine which brands of orange juice people prefer. The people are randomly chosen at the supermarket and are asked to taste both brands without knowing which brand they are drinking. So, I want you to come up with some flaws, and then how could you improve them? So, try that in 1, 2, 3. Okay, so here's something I came up with. Flaws, there could be volunteer bias because it's only people who actually want to drink the juice. And it's really hard to overcome volunteer bias, but I said maybe include a survey or focus group of people who have bought the two brands as added data to compare. So just extra stuff. Alright. If you put something different and you want to ask me if that's okay, you can send me a message. C. Decide if computer games are more effective than paper and pencil drills for children learning the multiplication tables. So you can think about this one. And 1, 2, 3. Alright, so really anything you put here is fine. So you could design your own experiment. Make sure you include random selection and addressing possible bias. But really, as long as you write something down, it makes sense, it's complete sentences, it's going to work here. Alright, so let me know if you have any questions.